In this video, we're going to introduce the notion of a Maclaurin series, which is a way to take a potentially complicated function and treat it almost as if it's a polynomial. So let's think, what's a polynomial and why do we want to do this? Recall that a polynomial is a function that you make just out of numbers and powers of x by multiplying those two and then adding them together. So something like 3x minus 4 is a polynomial. This is a polynomial of degree 1 because x raised to the first power is the largest power of x. Something of degree 2 would be x squared plus 2x plus 7. Now, these are very easy functions to manipulate. For example, if you want to find the value of a polynomial at a particular value of x, all you have to know how to do is multiply numbers and add them together. You don't need any special rules or special laws like you might if you were thinking about using a trig function or an exponential or a logarithm or something like that. Similarly, if we wanted to add these two together, all we do is add the x squareds. So in this case, the first one doesn't have an x squared, so we just get x squared. Add the x's, so we get plus 5x, and then add the constants, so we get plus 3. Now, the kind of function we're going to be dealing with is not quite a polynomial, but it's something called a power series. And the key difference between these two is that, as you can see, a polynomial has a biggest power of x. That's called its degree. That's where the polynomial stops. Well, a power series doesn't ever have to stop. So it's got something without any x at all, a0. It's got something with x raised to the first power, a1 plus x. It's got something with x raised to the second power, a2 plus x squared. Then something with x raised to the third power. And it just keeps going forever. And that's the difference between a power series and a polynomial. So a power series just goes on forever. This would be a difficult thing to deal with if we had to write down infinitely many terms every time we tried to deal with a power series, but instead we're going to use summation notation. So summation notation, you recall, has this capital sigma, that just means add. It's got lower indices. These tell you where to start adding. Upper indices, those tell you where to stop adding. And then the thing to the right of the sigma, which are the terms you're actually adding together. So for a power series, we're always going to start at 0. So I'll use n as my index. I start at n equals 0. I said that we don't ever stop adding terms together in a power series. That means the upper index, which normally would be something like 10, instead now we'll write infinity. And that just means keep adding terms forever. And the terms we're adding are a sub n x to the n. So if I plug in n equals 0, for example, I'll get a0 times x to the 0. Now x to the 0 is always 1, so this is really just a0. And that's the first term that I have in this power series here. If I plug in n equals 1, I get a1 times x to the 1. That's the second term in my series. If I plug in n equals 2, I get a2 x raised to the second power, and that's the third term. And this just continues forever. What we're going to study is what's called a Maclaurin series, which is a special kind of way to express a function as a series using the derivatives of that function at x equals 0. So to do this, we're just going to think a little bit about what happens when you take a series, take its derivatives, and plug in x equals 0. So here's my series. a0 plus a1x plus a2x squared plus a3x cubed, and it just goes on forever. And I'm going to go ahead and call this function f of x. And what I want to do is I want to think about what happens when I plug in 0, and what happens when I take derivatives and plug in 0. So first of all, f of 0 is an easy thing to figure out, because every time there's an x, that'll just become 0. So I've got a0 here, plus 0 plus 0 plus 0, and I'm adding on infinitely many zeros, so we're done. F of 0 is just a0, the very first term in my series. What happens then if we take the derivative of this series? Well, we want to treat these like polynomials, so we should take the derivatives as if this were a polynomial. That just means take the derivative of each term separately. If I take the derivative of a constant, that goes away. If I take the derivative of a1x, I just get a1. If I take the derivative of a2x squared, I get 2a2x. And then the derivative here will be 3a3 squared. And that'll just continue on. So if I take the derivative and plug in 0, I just get back a1 in exactly the same way that I got back a0 when I plugged in 0 to f. Let's do this one more time. Take the second derivative. So the a1 term is now constant, so it goes away when we take the derivative. When I take the derivative of 2a2x, I get 2a2. And then take the derivative here, I get 6a3x. And then there will be higher terms. So the second derivative evaluated at 0, it's not a2, it's 2a2. Similarly, if I took the third derivative and evaluated it at 0, it would be an expression involving a3, and it'll in fact be 6a3. So when we take the derivatives of a series and plug in 0, we don't just get back the coefficients that we started with. We get back the coefficients, but sometimes they have an extra number in front. And to fix that number, let's recall the number n factorial. So n factorial is the number n times n minus 1 times n minus 2, all multiplied down times 2 times 1. Now there are a couple special cases of n factorial. Most importantly, 0 factorial we just call 1. 1 factorial is also 1 because it's just 1 multiplied with itself. 2 factorial is 2 times 1, which is 2. And finally, 3 factorial is 3 times 2 times 1, which is 6. And if you went one step further, 4 factorial would be 24. And if you took this process 2 steps further, so we get to the fourth derivative, you'd also see some 24s appearing. So what we have here is we figured out that our series f of x is in fact represented by a new series where we've used derivatives evaluated at 0. So a0 is just f of 0. So f of x has the same constant term. It's just f of 0. a1 is what happens when you take one derivative and plug in 0. So if we take one derivative and plug in 0 and multiply by x, that'll be a1x. a2 x squared, well, 2a2 is what happens when you take two derivatives and plug in 0. So if we take two derivatives and plug in 0 and divide by 2, that'll give us a2. So then we can put an x squared. And then for the next one, we would get a 6a3. So we need to take three derivatives, plug in 0, and divide by 6, and then put an x cubed. And we could continue that process. And this is essentially what a Maclaurin series is. So we say that a function f of x has a Maclaurin series if we can write f of x as a sum of this form. So if f of x is equal to the sum from n equals 0 to infinity of terms that look like this. So what do these actually look like when we write it out in summation notation? Well, there's an x to the n. That's the easy part. And then we have this expression here. We've already talked about n factorial, and you can see the n factorial terms appearing in the denominators here. 0 and 1 factorial are both 1. That's why there are no denominators in the first terms. And then what's this? Well, if you write f with a superscript n in brackets, this just means take n derivatives of f of x. So if I take 0 derivatives, that's just the function. If there's a 1 here, that means take 1 derivative. A 2 here, take 2 derivatives, and so on. So this is the expression from Maclaurin series for a function f. Some functions have Maclaurin series, others don't. We'll see in the next video how to compute some and some properties that these have.